Hi, this is Robert Quimby, and I'm going to tell you about processing CCD images. So as an astronomer, when you go out and you take an image of the sky, what you're ultimately trying to do is to try to measure how much light you're getting from different sources in the sky. And so you want some number that is proportional to the amount of light that you're getting from each one of the sources. Now, that's not what you get when you take a CCD image to start with. You have to process the image to actually get that information. You have to remove bias and you have to correct for pixel-to-pixel variations. So what we're going to be doing is we're going to discuss the different forms of bias. There's two different sources of bias that we need to correct for in our images. We're going to find out that not all the pixels are equal. Some of the pixels are going to be a little bit more sensitive for different reasons than others. And we're going to need to correct for that if we want a number that's proportional to the number of photons. We got to get rid of these effects. And so through this process, we're going to talk about overscan, we're going to talk about bias, we're going to talk about flat field images, and how we can use these to take our raw image and fully process it to make the scientifically valid image that we want. All right, so let's begin by reminding you how CCDs work. Photons are incident on some detector area. They excite electrons in the valence band up to the conduction band, and then they get trapped in these potential wells that are set up by basically voltages that we regulate on the CCD. And by changing those voltages, we can march a bunch of charge that we collected at one pixel, one spot on the CCD, march that down and move it over into an amplifier where we can convert that, few electron volt signal into milli-electron volts, where we can actually then assign a value to it. We pass it to an analog to digital converter, takes those voltages, converts it into a number, sends it to your computer. All right. So the number we get on our computer, we're going to call that C. That's I'll call it counts, or sometimes ADU, analog digital units. And that number is going to be equal to several terms here. What we want is this term here. We want the number of photons that were incident. That's our n gamma here. But we're also going to have these bias terms. We're going to have a floating bias term, which varies with time. And we're going to have a static bias term, which is constant over time, but varies from pixel to pixel. And then there's also this gain factor here. So when we make these measurements on our CCD, it is converting those electrons into counts. And so there's some conversion factor, which we call the gain. So let's start off by looking at our raw CCD images that just fresh off the detector, and we'll see what that looks like. So I'm going to use Matplotlib here, but I'm going to use Matplotlib in notebook mode. So this is going to allow me to actually see the pixel values right here in the notebook. And so we're going to open Matplotlib. We're going to load a FITS image. So we need the AstroPy.io FITS package. And we're going to get this file raw.fits, which is in the media folder. So we're going to run all that, load in that image. And now we can display that image. So I'm actually going to pop out here so we can see this image a little better when I run this, because it's big. And okay, so here's now the image displayed in my browser. And what you'll notice is in the bottom right-hand corner here, when I move the mouse over, it tells me the XY position of the cursor of the mouse. And then it also has a number over here, which is the number of counts that was recorded by the detector. So this is the ADU number at this point. All right, so the detector that we have here is actually a 2K by 2K chip. That means it's 2048 pixels by 2048. But you'll notice we have it binned here. So we're binning 2 by 2. And that means that we're going from 0 to 1023 and 0 to 1023 here. But if you look carefully, you'll notice that there's actually a few extra columns here. There's extra columns, and these columns are not all, they look dark here just because of the way I have it scaled here, but they have different values. If you look at the numbers there, you'll see that there's 535, 534, 536. So there's a range of values in this strip here, but the pixel values in the detector area here are in the thousands. There's about 2,000, 1,970. So these just appear black here. So these extra columns here are actually not real columns. They're not actually on the detector. These are what are called overscan, and you can think of them as virtual pixels that are added when the image is read out. And this is an important part of calibrating the image because this is telling us what our bias level is. This is telling us when no light is incident on your detector, you're still going to get 536, 530 some odd counts in each one of those pixels. So the way this works, go back in this now, is that the overscan is actually added right on the chip during the readout process. So you might remember that when the readout takes place, so this is the little CCD demonstrator here, and you get photons that are incident here, and they get trapped inside one of these potential wells. And then by adjusting the voltage, we can shift them down, and we can drop them down into the serial register here. And then by marching these voltages over, we can move this charge over to the amplifier. So we'll do that. And then we can turn the amplifier on so that the charge can go over there. And now at this point, we have the charge on the amplifier, and then we can send it to the ADC. Let me just turn on one of these guys. That's what it would be. And once we do that, all the charge goes over to the analog to digital converter, and we get a number, 7. So that's how many electrons we got in there. And normally there'll be a gain factor here. So if we had 7 electrons, we might get a number which is 5 or 4, a different number than the actual electrons. It'll be multiplied by that gain factor, or divided actually. So we can get that measurement, and then we can clear the ADC, and we can actually continue this process. We can shift the charge over again. There's nothing left in the register, but we can keep doing that. And we can shift over again, and we can dump all the charge onto the amplifier. There's no charge. And then we can take a measurement. And this measurement will get appended to the end of our row of measurements. So what we do is we take one row and we step it down into the register. We read out each one of the columns in that row, and then we just keep reading out. We do another cycle so we can read out another set of pixels. And those pixels are what form the overscan. That's these pixels here. So these don't actually exist anywhere on the detector array. There's not like an extra column or anything. It's just it's just like this. So this is a 6x6 detector, and we can read out 6 columns in one row, and then we can read out 6 more without shifting any charge down, and we'll get a measurement of what our bias level is. Now this is helpful in measuring bias, which changes from image to image. Because again, the way the CCD is working is we have an amplifier here, which is producing a voltage, which is being measured by our analog to digital converter. And remember that voltages are relative. So we'll have some number of electrons, and we'll amplify that, and we'll get some voltage. But we can decide what the reference value is for that when we're converting this into a digital number by the ADC. So we can say that you have to have 15 millielectron volts to get 1, and then 30 millielectron volts will get 2. But we can decide where we're going to reference 0. So we can set the 0 level actually to be much lower than we expect to get. And then that first number, when we get 1 electron in there, instead of getting 1 count, we can get 500 counts if we want to. It's all just by how we bias our voltage here. So the overscan is giving us a measurement of the bias that we've put onto our detector. So this gives us a measurement of what we call floating bias, because this can change from exposure to exposure as the voltage there on the amplifier, that kind of bias voltage, drifts up and down. So we can correct for that. But there's a second type of bias, and this is the bias that is between one pixel and the next pixel in the detector. Those can also have a bias, and this can be the same over time, but it just has to do with how each one of those individual pixels is measuring and recording charge on there. It could be a slight voltage offset between one pixel to another. So we have to measure this as well, and the way we do that is we take a exposure with the CCD shutter, with the shutter over the CCD closed, so that no light is allowed to get in. And by doing this, we can just see what values we get on each one of those pixels without any photons being incident on there. So again, the counts that we're going to get on a detector is going to be a combination of the number of photons that were incident, and there's some factor here for how many of those photons are actually going to be converted into electrons. Not all of them will. Some of them will be incident on a detector, but they'll actually reflect back or even be transmitted through the CCD. Only some fraction, hopefully a good fraction, will be absorbed and turned into photoelectrons, Then we have this floating bias, which we just discussed, from biasing our amplifier. And then for each pixel, again, there can be a little bit of a bias on there. And this is all divided by the gain. So if we shut the shutter, so no light comes in, then this term here cancels out, and we just have these two bias terms. So we can measure this floating bias using the overscan, subtract that off, and then we're just left with this static bias. So let's take a look now at what that looks like. I've got a bias frame here in the media folder for you, so we can load this in. And let's pop out again here. And so here we go. So this may look like noise to you, and there is some noise in here, but there is also signal, and that's the important thing here. The bias is not noise. It's not a form of noise. It's primarily a signal. And the difference here is that that's not totally a random effect. This means that from image to image, you tend to get a certain number more counts in one pixel than you do in another. And this, on individual images can vary, but on average, there's going to be some pedestal difference between these two. And you can see this most clearly if you kind of zoom in down here on this corner here. So I'm going to click on this box, and I'm going to zoom in like this. And as we zoom in, maybe I'll zoom in a little bit more here. Okay, so we're just looking at the first 70 columns and 60 rows. And you'll notice that this bottom edge here is darker, a little darker here on the side than these other pixels here. And if we actually look at those values, we can see that the typical values here, again, around 530. That's kind of the bias level for this CCD. But down here, these numbers are a little bit less. So these are low 529, 531, whereas up here it's actually 540. I should have said 540 before. That's the typical number up here, 540, and down here is 530. So what this is telling you is that these pixels down here start off, even with no photons on it, they start off a little bit fainter apparently than these other ones. And this is not a real signal. This is not telling us that the sky is brighter or fainter in here, because we're not looking at the sky. It's just telling us we have a bias in our system and we need to correct for this. So we want to measure what this signal is, this bias signal is, and we want to remove it, but we got to keep in mind that every time we make a measurement, there's going to be noise associated with it. So every time we take one of these bias exposures, one of these 0-second exposures, we're going to get a value for, say, this pixel here. And when we take the next exposure, we're going to get probably a different value for that pixel. And over a set of exposures, there's going to be some scatter in what those values are. Now that's noise. When we measure the same thing over and over and we get different results, that's noise. So what we can do is we can make multiple measurements for what the value of this pixel is just by taking multiple bias exposures and then taking an average of that, and that'll average out all that noise and give us the best measurement of what that value should be. And that's what we want to use when we're correcting our CCDs. So we take multiple values, and then we can actually combine all of these to make one measurement for each one of those pixels. So what we typically do is we'll take something like 25 of these 0-second exposures, no light allowed to enter the CCD, and then we'll subtract off the overscan because we want to get rid of that floating bias, which could in principle change from exposure to exposure. And then we can get rid of those overscan columns once we've done that step. We don't need them anymore. And then for each pixel on the CCD, now we have 25 different measurements of what its value would be after overscan subtraction. And what we can do is take an average of those 25 values. And that will give us the best measurement, the best guess we have for what the value, the bias value is of that pixel, the starting value of that pixel after overscan removal. And then we can do that for the pixel next to it, and the pixel next to it, and the pixel next to it. We can do that for every pixel on the array, and we'll get ourselves a measurement of what the static bias is from pixel to pixel across the array. And this is actually pretty easy to do with NumPy. So after we've got our bias removed from our image, we still are not done yet. We still don't quite have what we want, which is this number proportional to the number of photons that were incident at the top of our telescope, the top of our system. This is what we want. We want this number here. We have counts here. That's what our computer is giving us. We've subtracted off the floating bias now. We've subtracted off the static bias. And we can actually measure G here. This is the gain. We can measure that in the lab just by doing some experiments on CCD. And we have just one value here for that one amplifier. We can figure out what that is. And then we have everything except for epsilon here, this quantity here. This is giving us the efficiency of our individual, each pixel on the CCD. And this is actually, it's possible to measure, but it's very difficult. You can do this in a laboratory setting, but on the telescope, out in the fields, taking measurements in the sky, this is very, very hard to get exactly. So actually, we don't measure this. What we do instead is we use a trick, which is we don't need to know the absolute efficiency of each one of our pixels. All we need to know is the relative efficiency. All we need to know is that this pixel over here on the array compared to this pixel over here on the array is, this one is maybe 90% as efficient as this one over here. Or more to the point, this one is 90% efficient compared to the average efficiency over the whole array. That's really all we need to do. And we can do this because all the measurements we're going to be making are relative measurements. When we say what's the magnitude of an object, we're saying how bright is it relative to some standard object, right? Maybe Vega, or maybe some other made-up standard. All we need is that relative number. So as long as we have the relative correction from pixels in one spot to pixels in another spot, we can find that number. So the key here is that we're not going to measure the efficiencies for each one of our pixels. We're going to figure out a number that gives us the average efficiency, and then the ratio of these. This is actually what we can measure here. We can measure the ratio of those two, and then once we have that relative efficiency, we're good. So how do we actually go about doing that? How do we find this relative efficiency? Well, first, let me make things slightly more complicated to start. Let's go back to this equation we have for the counts that we get on our computer. So this is after the CC has been read out. We have some number of counts, and that's going to be the sum of the bias values and the number of photons we get in there, less this efficiency factor divided by the gain. Now, what I've done here is I've added these indices I and K. These are indices on. This is not the kth power here. I'm not saying C to the kth power, and this is not base I or anything like that. These are just simply indices. So this is telling us, the I value tells you where on the CCD are you. You can think of this as the XY position on the CCD. And K here tells you which exposure are we talking about. The first exposure, the second, the third, the fourth. Those are different values for K. So K is 1 or 2 or 3 or 4, just like I could be some combination of X and Y values. Okay, so I write it this way because I want to show that there are some quantities here that depend on position on the array, and there's some values here that depend only on time, right? And by separating those terms, we can actually get out what this efficiency is. Okay. So the first thing we can do is we can look at this and we say, well, we've already been working with two different bias terms, right? This is actually contained in here, but we can split those back out. We can say that our bias is made up of a floating bias, which changes with time. That's why it's a superscript. And also there's a bias term, which is pixel to pixel dependent. And that's why this has no time, because it doesn't vary in time, but only spatial dependence here. Then the other thing we can do is say, well, we only have one amplifier on our CCD. We could have more, but we're considering an amplifier, a CCD with one amplifier here. And this means that all the pixels on the array are going to be read out with that same amplifier. They're going to have the same gain. Right? So there's no spatial dependence on the gain. All the pixels see the same gain. And also the way the electronics work is the gain tends to be very constant. So it can drift a little bit over time, but not very much. So we're going to ignore that and say that the gain is just constant with time and space. All right. So now here's what we can do. We can set up an experiment where we try to uniformly illuminate our detector. That means we'll just point the telescope at a field that has nothing in it, just a blank field, where we're getting light, we're getting photons, but at every spot, at every angle that we can measure, we'll get the same number of photons, ideally. If we do that, then we have this term that is the efficiency times the number of photons we get. And the number of photons is going to be constant over space, so we can get rid of that indice there. It could change with time, from one exposure to the next exposure. Maybe we're doing this experiment by we're illuminating a screen and we're taking a picture of that screen. This is something you might see inside a dome. You might see a screen that has a light projected onto it. The amount of light we project on there, we try and make constant, but over time, the lamp can heat up a little bit and get a little bit brighter, or it can cool down, and that can actually affect this number a little bit. So we're going to leave that dependence there. And the other thing we can say is that the efficiency is also going to be roughly constant with time, right? So it may vary from pixel to pixel, but over time, it's going to be essentially constant. So now what we can do is we can take an average, right? So we've got every pixel in the array we're trying to, at the top of the telescope, we're projecting the same number of photons down. Each one has a different efficiency though, so we may get different values recorded on each one of those pixels. And we can take an average though. We can say the average product of the efficiency with the number of photons that were incident at the top of the telescope. We just take the sum of each one of the pixels we have, that product, divide by the number of pixels we have, and we get an average. Okay? And in calculating this average, we can again note that this quantity, the number of photons we get, does not depend on spatial locations. We can pull that out and we can see it. This is really just an average of the efficiencies for each one of those pixels. So we can write it this way. We can say that we can get a quantity which is the number of photons incident times the average efficiency of the pixels. And this is something we can measure, right? We just take an exposure where we have uniform illumination and average over all the pixels, and this is what we get, this quantity here. So we don't actually know the number of photons that are incident. That's hard to measure. We don't actually know the efficiency of any given pixel, but the average of the whole system, we can measure that. And so once we have that, now we can actually figure out what the relative efficiency is of each pixel on the detector. So we can go back to our equation, we're relating the counts that we get on the computer to the number of photons that were incident. And we can say, how does the efficiency of one given pixel relate to the average of the entire array? And so all we do is we just take the counts that we get from our computer, subtract off the floating bias and the static bias, multiply the counts, of course, by the gain, and just divide that by this number that we can calculate, this average efficiency times the number of photons incident on the detector. And this ratio here gives us this quantity, which is what we want. This is the efficiency for any given pixel. Right? So again, these are all things we can measure. We can look at one pixel that we've taken this kind of flat field image with and look in that flat field at one pixel, and we can get this quantity here, the ith efficiency times the number of photons, divided by the average of the whole image. Right? Again, this is just one pixel's number. This is the average of the whole array. And that gives us this for every pixel in the array. So once we've measured this, once we have this flat field efficiency for each one of the pixels in our array, we can apply that to get what we ultimately want, which is the number of photons from a given source. Actually, the relative number of photons. We can't get the absolute number because we don't have the absolute efficiency. But if we look at two different pixels on the detector, say the ith pixel and the jth pixel, we can figure out what the ratio of these two is. And that's just given by the ratio of the counts we get minus the bias. And then we use this ratio of the efficiencies to scale them. So let's look now at an actual flat field image so we can get some idea of what we're working with here. So in the media folder, again, there's a flat.fits file. I'm going to load this in. Okay, and here's what that looks like. So this is actually an image that we took during twilight. So the nice thing about twilight is the sky is still fairly bright, so you get a lot of photons in. But the light you're getting is not mostly from individual sources. It's mostly just scattered light. And that scattered light tends to be roughly constant as you move from position to position, at least over the small field of view of our detector. So over a few arc minutes, this holds up. Over larger scales, it doesn't. So we just look kind of opposite the direction of the sunset. We'll see how many counts we get on each pixel, and we can use this to correct for the pixel-to-pixel variations in the sensitivity of the system. Now you'll notice looking at this that we didn't completely succeed in getting a completely uniformly illuminated field. In fact, there are stars that we can detect readily in this image. So this one image here isn't very good for doing flat field variations, for mapping those out, because the counts we got here, natively, there's more counts coming to this pixel than there were to this pixel over here. Here we're getting the light from just the sky, and here we're getting the light from the sky plus some star that happens to be on that spot of the sky. So what we do when we're taking these images is we don't just take one. We take a whole set of these, and each image we move the telescope a little bit. And what that does is it moves the stars to different positions on this detector. And then if you consider just one pixel, you can say, okay, in this first exposure here, we got hit by a star, but in the next exposure, you're not likely to get a star on it. If you look here, there's a few stars in this image, but most of the detector, a vast majority of pixels here, have no starlight affecting them. So if we take 5 different images and we move the telescope each time, probably at least 4 of those are going to be good measurements of how bright the sky is without any starlight. So we can just take, a simple thing to do is take a median of all 5 of those images, and then for each pixel, we'll be rejecting the starlight, and we'll just get kind of the typical amount of light from the sky. And that should be uniform across the field. And so that will give us our pixel-to-pixel efficiencies, and we can use this with our bias, and we can put it all together, and we can completely process our images. So this process is sometimes called image processing or detrending your data, but it's just generally removing all of the effects from the detector, from your telescope, and trying to get numbers that are proportional to the number of photons you got from the sky. So to do this, we remove the overscan, right? Removing meaning first we subtract off its average value, and second we actually clip it off because it's not real pixels there. We don't need them once we've measured what the value is in there. So remove that off. Then we can subtract off the bias, and we take that stack of biases because we want to have the best measurement possible without any noise. We don't want to add noise. If we subtract that off, and then we divide by our master flat, which again is a stack of a bunch of images, each one pointed at a different spot, so that we don't have things like stars or particle events affecting our measurements. And once you've done all this, you've got a nice detrended image, and you're ready to do some science.